Hello everyone, welcome back to MA1103 Business Mathematics 1, and this is the last topic in this course, and I am Renovia Simanjunta. So today we will learn about permutations and combinations, which is the last subchapter in chapter 6 from 10th textbook. Okay, what is a permutation? So if you have a set, then a permutation of that set is an arrangement of the objects of the set in a definite order. So the keyword here is in a definite order. So you can see here the order of which objects are arranged is very important. Yeah. For instance, if you have ravel, yeah, if the winning ravel is 9237, of course the other ticket with number 2973 is not a winning ticket, right? Yep. So again, the order of arrangement is very important in permutation. So let's say we have a set with elements A, B, and C, and then we want to know the number of permutation in A. So because we have three elements and we want to arrange it, let's just denote with this blank space here. Yeah, so we have three blank spaces, so each of them has to be should be filled with either A, B, or C, right? So now if we see the first blank spot, yeah, it can be filled with either A, B, or C, right? So there are three possibilities in the first blank spot. What about in the second one? The second one, because we already use one of A, B, or C, then of course there are only two objects remaining, right? So we can only use those two objects to choose, yeah, the element that will be put in the second blank spot. So we have two possibilities here, and then of course because we have already used two elements of A, then we are left with only one element, right? Yeah, so altogether, yeah, because this is, remember, this is a consecutive task, yeah, so one is conducted after the other task, then we can use the multiplication rule, right? So we have here the number of permutation of A is 3 times 2 times 1, which is equal to 6. All right. So now we want to list all the permutations of A with the aid of a tree diagram. Like before, we want to fill in the first blank spot first, yeah? So there are three possibilities, A, B, and C, right? And then because we already filled the first blank spot with A, of course, the second blank spot can only be filled with either B or C, yeah? And similar here, either A or C, and here, either A or B, yep. And because we already use A and B here, of course, the only possibilities is using C, yeah? That's the remaining possibilities, the only one. And here, B, and here, C, here, A, and here we have B, and here we have A, right? Okay, so if we want to list all the permutation of A, it will be A, B, C, and then A, C, B, and then B, A, C, B, C, A, C, A, B, and the last one is C, B, A, yeah? So as we have counted in the part A, there are 6 permutations of A. Okay, so let's see this example now. So we have a basketball team consisting of 9 people, and they want to take a group picture, right? And now we want to know how many ways that these 9 people can be arranged, yeah, in order to have a line for a group picture. So now we have this 9 position. The first one, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. And then how many ways can we fill the first position? The first position, of course, there are 9 people. We can choose one of them, either one of them. So there are 9 possibilities, yeah, or 9 number of ways to fill the first position. What about the second position? Because one person already filled in the first position, then of course 8 possibilities or 8 number of ways for the second position. Similarly, 7 here, right? 6, 5, 4, 3, 2, 1. And again, we can use the multiplication principle, yeah, to count the number of ways for arranging all of this, yeah, to arrange this line for the group picture. So we have altogether the number of ways in which the team can arrange themselves. The team, sorry. Is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is equal to 300,062,880. Yeah. So there are many number of ways for them to arrange themselves in a line for a group picture. Okay. So in general, what is the number of a permutation? Yeah. So now we have a set A of n distinct objects, and we want to take n of them to make an arrangement which is a permutation. Yeah. So how to do that? Fill the first blank, yeah, the first blank position with n ways, the second one with n minus 1 way, and so on and so forth. And then altogether we will have this one, which is n times n minus 1 times n minus 2, and so on until times 1. Okay, so that's the way of permuting the elements of the set A. Okay, so to simplify the writing of that multiplications, of course you don't want to write it in that way, right? N times n minus 1 and so on, yeah? What if you have a big number, 100 for example? You don't want to write 100 times 99 and so on, yeah? So it is defined what we call the n factorial for a natural number n, which is equal to n times n minus 1, n minus 2 times 3 times 2 times 1, yeah? And we call it the n factorial, and it is denoted by n with an exclamation mark, yeah? So that's for a natural number. But for 0 factorial, we define as 1, yeah? So it is equal to 1. So this is defined. Okay, so now what we have done before, yeah, for the number of permutation of n distinct objects taken n at a time, it is just n times and so on until 1, and it is equal to the n factorial, yeah? Yeah, and then we denote that permutation as p and n, yeah? So now what about if we don't want to take n at a time. We don't want to take n object at a time, but less than that. Yeah. So if we want to take only r object at a time, yeah, then we denote the permutation with p and r. And then of course we only have r blank spots, yeah, because we take only n object, only r object, yeah, but we have n possibilities taken r objects. Okay, so r blank spots, yeah, and we fill in starting with n minus 1 and so on, and the last one will be n minus r plus 1, right? Yeah. Okay, and if we write it down as factorial, in factorial term, it will be n factorial divided by n minus r factorial, and this is the p and r, which is the number of ways of permitting n distinct objects taken r at a time. Okay, so now we want to compute P44, yeah. So what is P44, remember? P44 is just 4 factorial, yeah, which is equal to what? 4 times 3 times 2 times 1, which is just 24. Okay, what about P42? P42 is just 4 factorial divided by n minus r, yeah, so 4 minus 2 factorial, so this is going to be 4 factorial, this is 2 factorial, yeah, and then of course this one is 4 times 3 times 2 times 1 over 2 times 1. We can cancel this part and we will get 12. So what is the interpretation of this? This is just saying that the number of permutations of 4 objects taken 2 at a time is equal to 12. All right. What about this way? What about this example? Yeah. So we have a committee, and the committee has a chairman, vice chairman, a secretary, and a treasurer. And this committee has 8 members, right? All right. So first of all, of course, we have to convince ourselves that this is a permutation problem. Yeah. What does it mean? It means that in this case, order is important. Yeah. So why is it important? Yeah, because there is a difference. Yeah, when we have someone, say A as a chairman and B as a vice chairman, with B as a chairman and A as a vice chairman. Yeah. So in this case, order is important. Yeah, so we can use permutation. The second question is, of course, how many objects are there to be permutate? Yeah, because the committee has 8 members, of course, the number of objects is just 8. So n is equal to 8. Yep. And then the last question will be how many that we will take to permutate. Yeah. So here there are how many positions? 1, 2, 3, 4 positions. Yeah. So the permutation that we want to count is taken 4 objects from 8 objects, right? So it's got to be P of 8,4, or it is just equal to 8 factorial over 8 minus 4 factorial, and this is equal to 8 factorial over 4 factorial. Yeah, and you can see here that 8 factorial is just 8 times 7 times 5, then times 4, 3, 2, 1, and so on, and that's just 4 factorial. Yeah. Oh, I missed 6 here, yeah, so it's supposed to be 6. Okay, over 4 factorial, we can cancel this, and then that will be equal to 1680, right? Okay, So that's about permutation. But sometimes we can have a set where the objects are not all these things. Yeah. So we have a set of n objects where n objects, n1 objects are alike, n2 objects are alike, and so on until nm objects are alike. And of course, if we add all of these objects, it should be equal to n. Yep. So how do we count the number of permutation of this n object taken n of a time? Yeah. Because there are n1 similar objects, n2 similar objects, and so on. So we cannot use the previous formula for permutation Pn. Okay, so say the number of such permutation is x, yeah? So if we have distinct objects instead of similar objects, yeah? So if we have distinct object instead of similar object, of course the number of permutation for this n1 object is n1 factorial, yeah? And it's the same with n2 and so on. Okay, so of course, if we count the permutation of the n object, if we consider this as distinct, it will be just x times n1 factorial, n2 factorial, and so on until nm factorial, right? And of course, now we can solve it for x, and x will be equal to n factorial over n1 factorial, n2 factorial, and so on until n factorial. Yeah. So remember, x is what? X is the number of permutations of n objects taken at n at a time, but we have these properties of the n objects, yeah? So n1 of them are alike, n2 of them are alike, and so on until nm of them are alike. Okay, so let's see one example. So we have here the word Atlanta, and we want to know, yeah, the number of permutations that can be formed by using all the letters in this word. Yeah, you can immediately see that there are objects which are alike in this word, right? For instance, what? For instance, the letter A, although it appears 3 times, they are just alike, yeah? And it is also the same with the letter T. Yep. So how many objects do we have now? Of course, altogether we have n, which is 1, 2, 3, 4, 5, 6, 7. Yeah, we have 7 letters. So here we have n is actually equal to 7. Yeah. But then we have the letter A, and there are 3 of them. So we say this is the first one, yeah? The first objects which are alike. So n1 is 3. What else? We have T. Say it is n2 is 2. And then we have L. So n3 is 1. What else? We also have N. And 4 is 1. Yeah. So how many permutations do we have? So, of course, we just use the formula, yeah? There are how many permutations? So, add all together, yeah? N factorial over, yeah? N1 factorial times N2 factorial times N3 factorial times N4 factorial. And of course, we have here what? 7 times 6 times 5 times 4 times 3 factorial, yeah? So we can cancel that one. And of course, we can divide 4 with 2. Yeah, 2 factorial is 2 times 1, so it's 2. So this is 2, this is 1. And all of this is just 1. So we have 420 permutations. Okay. So that's the first example. What about the second example here? Yeah. So we have a firm, a stock brokerage firm, and it received 9 inquiries getting new accounts. Yeah. And then they want to direct those accounts to 3 of the firm account executives. Yeah. And each of the account executive handle 3 inquiries. Right? All right. So these 9 inquiries. Yeah. So of course we have n is equal to 9. Yep. Then 3 will be handled by one account executive, yeah, another 3 by another account executive, and another 3 by another account executive. So they are alike, yeah, those 3 are alike. So we have n1 equal to n2 equal to n3, which is equal to 3, yeah. And of course we just have to use the formula, yeah. So here the inquiries can be directed in how many ways? 9 factorial over 3 factorial over 3 factorial over 3 factorial, yeah, which is just what? 9 times 8 times 7 times 6 times 5 times 4 times 2 factorial over 3 factorial, 3 factorial, 3 factorial. We can cancel this. And then 3 factorial is just 3 times 2 times 1. Yeah, so it's 6. We can cancel this. And then we can cancel which part? Maybe this one, yeah. We cancel the 3. So this is just 3. And then we have 2 factorial. Yeah. And then with this one, we have 2. Yeah. Okay. The result will be 1680 ways. Alright, so those are the examples for permutations where we have objects which are alike. Okay, the second type of counting is what we call combination. Yeah, if in permutation, order is very important, in combination, order is not important. Yeah, so for instance, if you choose hand in a poker card, yeah, so it doesn't matter the order of which the card appear, right? So here in the left hand side, yeah, ace heart appear first, yeah, where in the right hand side ace heart appeared last, yeah, but it doesn't matter, they are the same hand. Okay, so now what about the number of combinations of an object taken R at a time? Yeah, we denote this by C and R, or maybe you can use this notation. Yeah, so imagine we have permutations, yeah, permutations of R objects, yeah. So this is R factorial permutation. Yep. And then if we take our object, yeah, and then we change the order, we get another R objects, and so on. Yeah, we change all the object. Yeah, but actually for combination, all of these are just the same. Yeah, the order is not important. So here we have C and R boxes of these R objects. Yeah, okay. So each of these can be permuted in R, X, and ways. And then of course we have then the permutation is equal to R factorial times the combination, right? And okay. What about the CNR now? Yeah, we just have to move the R factorial to the right hand side, and then we have this. Yeah, n factorial over n minus R factorial is the PNR, and then divided by R factorial. Yeah, so this is the number of combinations of n objects taken R at a time. All right, let's see one example. We want to count the C44. Yeah, C44 is of course just 4 factorial over 4 factorial, 4 factorial minus 4 minus 4 factorial. Yeah, so this is 4 factorial over 4 factorial, 0 factorial, and we can cancel this, and 0 factorial is 1, remember? So this is just 1. Yeah, so if we have combinations of 4 distinct objects taken 4 at a time, there will be just one way to do so. What about C42? C42, of course, is equal to 4 factorial over 2 factorial, 4 minus 2 factorial, and then this equal to 4 factorial over 2 factorial, 2 factorial, and we can see this is just 4, 3, 2, 1, this is 2, this is 2. Of course, we can cancel this, and the result will be 6. Yeah, so what does it mean? It means that the number of combinations of 4 distinct objects taken 2 at a time is 6. Okay. So now, again, we have an example of forming a committee. Yeah, but different with the one that we have before. In here, order is not important. Why is not? Why it is not important? Because there are no certain position in the subcommittee. Yeah, so everybody is just the same in that subcommittee. So order, of course, is not important. Yeah. So how many members do we take the selection from? 10 members. Yeah. So n is equal to 10. What about the R? How many should we take? We take 4 members. Yeah. So of course, the number of ways in which this can be done is combination of 10, 4, which is what? 10 factorial over 4 factorial times 10 minus 4 factorial, and this is just 10 factorial, 4 factorial, 6 factorial, and remember you can cancel 10, part of 10, yeah, 10 factorial with 6 factorial, so we have 10, 9, 8, 7, the 6 factorial has been cancelled, and here we have 4 factorial, which is 4, 3, 2, 1. Yeah. Okay, we can cancel these 2, then we can cancel this with 3. Okay, so altogether we have 210. So the number of ways that we can form this investigation subcommittee is 210 ways. All right. The last question will be, how many poker hands of 5 cards can be dealt from a standard deck of 52 cards? Yeah. So remember, this is the first illustration we have about combination, that a hand in a poker card, the order is not important, right? Okay, so we use combination. So it is combination of what? Combination of course, we have 52 cards, and then we take 5 cards. Yeah? And of course, this is equal to 52 factorial over 5 factorial. So 52 minus 6 is what? 47 factorial. Yeah, so you have here what? 52 times 51, 50, 49, 48 over 5, 4, 3, 2, 1. And this is gonna be 2,005,989,60. So there are so many ways, yeah, to deal 5 cards from 52 deck of 52 cards, yeah, in a standard deck of poker. Yeah, so many possibilities. All right. And of course, yeah, sometimes we need to use more ways of counting, yeah. So not just permutation, not just combination, but maybe we have to combine those two. And also maybe we can use also the other rules, for instance the multiplications principles. Okay, so here we have a string quartet consisting of 2 violinists, cellists, and this quartet will be selected from a group of 6 violinists, 3 violists, and 2 cellists. Yeah. So in how many ways can the string quartet be formed, right? Okay. So first of all, of course, we have to choose the violinist. Yeah. To choose the violinist, we choose from how many? From 6, and then we choose only 2, right? So here we have the violinist can be selected in how many ways? Combination of, we take from 6 and then we take 2, right? Yeah, so this is, yeah, if we count with the formula 6 factorial over 2 factorial times 4 factorial, it will be 15. What about the violist? Yeah, this is can be selected in how many ways? We have only 3 violists and we need one of them. Yeah, and if you count it, it will be 3 ways. What about the cellist? Yeah, can be selected in how many ways? Again, we have 2 cellists and then we choose one of them. So this is equal to 2. So we use combination here. And what about forming the string quartet? Yeah, of course, we have 3 tasks here. First, you choose the violinist. Second task, choose the violist. And then last task is choose the cellist. So we can use the multiplication principle. So altogether, there are 15 times 3 times 2, which is equal to 90 ways of forming the quartet. Okay? All right. So now if we have one of the violinists is to be designated as the first violinist, and the other is second violinist, yeah? How many ways? Is it the same with part A? You can see here that because here one of the violinists will be designated as the first violinist while the second one is at the second violinist, in this case order becomes important, right? Okay? Yeah, because if we choose one, he or she will be the first violinist, and then we choose another one which will be the second violinist. If we switch the order, it will give us the different result. Okay, so now the violinist can be selected in how many ways? This is not a combination anymore, yeah, because order is important. So now it's for P62, sorry. Yeah, and this is equal to 30. Right? What about the other? Yeah, the others, the number of ways of selecting them are just the same, yeah, for violins and cellos, right? Yeah, there's no difference. So altogether, to form the string quartet, we have 30 times 3 times 2, or this is equal to 180 ways of forming the quartet, right? Okay, so that's an example, and then there are two exercises here for you to think about and to discuss later. Okay, so that's the end for subchapter 6.4, permutations and combination, and this is also the end of MA 1103 Business Mathematics for this semester. Thank you for your attention, and I'll see you again next semester maybe, and have a good day.